We just talked about how to take a very simple filter with one term, z to the minus 1, and that was our transfer function, h of z. How to do that and show that basically in that case the output represented a time-delayed input. However, usually our transfer function is a little more complicated than that and can have numerous terms, often higher order terms in z. And so it's convenient because of the time shifting property. When we write a transfer function in the z domain, because our z transform places the output in negative polynomials of z, the transfer function in the z domain is written as a polynomial in 1 over z. And so in the most general case, our transfer function would look like powers of 1 over z in the numerator and the denominator. And so, unlike the Laplace transform, where when we have a transfer function in S domain, we always want the order of the denominator to be higher than the order of the numerator, otherwise the system is unstable. In this case, stability is not really a function of the powers of z in the numerator and denominator in the same way that it is for the Laplace transform. So, the goal of this exercise is to use the time delay property to see what the coefficients of a typical polynomial in H, what that really means in terms of input and output. So first, let's look. The first line here is what we just referred to, that in general a transfer function has a numerator and a denominator, and polynomials in both the numerator and the denominator. Polynomials in 1 over z, so these are just written as negative powers of z. And there's some order in the numerator and some order in the denominator, and we don't know what that order is. It can be anything. The only thing that is typically done is the denominator is arranged in such a way that the first term in the denominator is a 1. So that's the usual way of doing things when expressing transfer functions of filters in the z domain, and you'll see why shortly. So whatever this constant was, or whatever this was, we do some algebra so that this constant now becomes 1 plus some polynomial in 1 over z. So we could abbreviate how we write this and write it as a sum over k terms in the numerator in powers of z to the minus k, and a sum over L terms in the denominator, powers of z to the minus 1. And then remembering that h of z represents y over x, or that basically this is the relationship between x and y, where once again x is our input, y is our output. We can do a little more algebra substituting y over x for h, and then multiplying through so that we don't have any more fractions. And when you do that, you see that this sum that came originally from the denominator is multiplying y terms, and this sum, which came originally from the numerator, is multiplying x terms. So one of those sums is going to multiply our output terms, the other sum is going to multiply our input terms. So we can simplify this a little bit further, because what we really want to do is we really want to see the effect that this filter transfer function, this filter, has on the actual output in space. So we really want to take the inverse transform of this. So we're going to start with that previous equation that we just illustrated on the previous slide, and I've repeated that here. We're going to start with that equation and just repeat it. And the first thing that we can remember is that we arranged our transfer function h such that the first term in this polynomial in the denominator was 1. And so because we know that that first term was 1, we can actually come in to this term that represented the denominator of the transfer function, and we can pull the first term, the 0th term, which would correspond to z to the 0 power, or the constant. We can pull that out because we know it's 1. So the 1 comes out, and that means that the sum, instead of going from 0 to L, Now the sum is going to go from 1 to L. So just a simple step of changing the range of the sum and pulling out the 1 because we know it's 1. So now what we can do is multiply, do a little algebra. So let's go back, and what we're going to do is multiply these two terms each by y of z, and then we're going to get y of z by itself. Now why would we want to do that? We would want to do that because y of z is our output. So we now have our output of our filter in terms of some other stuff. Okay, two terms, two summed terms in z. So now what we want to do for each of these sums is consider a simple case where we're going to look at what's going on with the nth term. So we're going to let the k in here go to n. B of k is going to go to b of n. And z to the minus k is going to go to z to the minus n. We're just going to look at what's happening in the nth term. So if we pull out the nth term, which is represented here, so this represents the nth term in that sum. If we pull out the nth term, we see that what we have is we have the transform of something times a constant times z to the minus n. And so what we can do is apply the time shift property where we realize that since we've got z to the minus n times a term that represents the z transform of x, then we can pull this term here inside the brackets. And so now we have this same coefficient, and now we have a time shifted term. Your textbook author plays a little loose and fast with his n and k indices. We evaluate for the nth term, but then we realize we're going to plug that back into the sum, and so it actually n goes back to k, which I understand is very confusing, but that's just the way the labeling is in the section. So so when we recognize that this multiplication by z to a power is actually a time shift, then we can represent that as the transform of a time shifted variable in the n domain, and so shifted by k, and then k is going to run through all possible values including this nth term that we pulled out. And we can do the same for the a terms, the coefficients multiplying the y terms, and when we do that, and remembering this sum is only running from 1 to L, this one running from 0 to k, when we do that we can express y also as a series of shifted values where the shifts are changing from 1 to L, whatever L is. So now the thing is, we have everything where we have either a straight function of z, which would be very easy to take the inverse transform, or something expressed as the transform of something. And of course, when we take the inverse transform of that, we just are going to get what's inside the brackets and some constants. So because the transform of a constant times a function is the constant times the transform of the function, we can take the inverse transform of this entire equation. And when we do, we'll get the inverse transform term by term, and here it is. And so this is really where we want it to be. Where we are now is we have the output, y of n, and we have that expressed as two sums. One is a sum over the inputs. Remember, x are the inputs. The other is a sum over the outputs. Now if you look at the sum over the inputs, what does it mean when k is equal to 0? When k is equal to 0, that's going to mean we have no delay. So the output here is a function of the current input, whatever that is, and all the delayed inputs, each multiplied by a respective weighting value, minus the sum over delayed outputs. And notice here that the sum is running beginning with 1. So that means that the current output can't be a function of the current output. The current output can only be a function of previous outputs. So our output variable, it can basically be expressed as a weighted sum of current and previous inputs and previous outputs. So that's a very significant result, and it's a general result. And depending on the values of the A's and B's and whether or not they even exist, because it is possible to have only B's, it's possible to have only A's, we're looking at different kinds of filters and different filtering approaches.